Okay, last video, and I don't think I got to any of these in class. So, all right. So the first one, I totally modeled this off of the Newton's cradle I have that y'all have seen before. Okay, that didn't work. Where you got the little steel balls that are hung from, I guess they're kind of like plastic wires. And as long as they're hanging there still, okay, it's suspended, it's not moving, then we're going to do our forces being balanced with each other type activity here. So I've got a force of gravity downwards on my steel ball, and then I've got these two tensions. These are both, they're the same material, they're the same angle to the ball. So each of these is going to contribute half, more or less, to offsetting force of gravity, if that makes sense. Okay, you've got half your force here, you got half your force here, offsetting this. And we're going to have to think about components there, okay, because those two components are going to offset force of gravity. So it's really this one and this one, because I've got two lines holding the steel ball. So FG really equals, I guess we'll call it 2ty, 2 times ty. And these are my ty's. Okay. My force of gravity also equals my mass times g, and my ball has a mass of 0.065 kilograms. Oh, why does that keep happening? 0.065 times 9.8 equals 0.637 newtons. Okay. And then ty. So I want tension in each cable. I want to solve for T. Okay. So really T is going to equal my sine of my 60-degree angle. So these are at a 60-degree angle. I think I forgot to say that. So T, let's see. Let me go back. Sine of 60. Go back a couple of steps. Sine of 60 is going to be Ty over T. And so Ty equals T times sine of 60. Okay. And then Ty also equals 0.637 divided by 2 here, because I know that those two are offsetting the force of gravity. So that's 0.3185 newtons. So then I can shift this around to solve for T. 0.3185 newtons divided by the sine of 60 gives me I'm just going to round to 0.368. Okay. So the tension in each of these little lines is 0.368 newtons. And if I went back and multiplied that by, let's see, if I multiplied that 0.368 times sine of 60, and I multiply that by 2, that's going to give me my original force of gravity. So that's balanced. This is balanced by the y components of each of these. Horizontally, I'm not moving. I have a horizontal component of each of these. They just equal each other out, and none of it's moving, but we don't really have to worry about those. That's not what we were asked for. So, okay. Another one, suspendy object with cables and such. This one's going to be similar to the wrecking ball. I got an object suspended. It's horizontally attached by this cable, and then it's also attached at an angle by this cable. And we actually want to get T1 and T2 here. Okay. So this similar to the one I did before like this, we got a force of gravity pointing downwards. We're going to have components of this T2 over here. So we're going to have a T2X and a T2Y. we're going to see that FG equals T2Y because they're balancing each other. And FG is also 980 newtons because I'm 980 because I'm going to multiply 100 by 9.8. And then T1 over here equals T2X, my X component over here. Okay. So similar to what we did in the last problem, I'm going to use tangent. This is a 50-degree angle. So I know that tangent of 50 is going to be equal to my opposite, my T2Y, divided by my adjacent, my T2X. Okay. I know that T2Y is 980. So I'm going to shift some things around here. I'm going to solve for T2X. That's going to be 980 divided by the tangent of 50. Okay. And that's going to give me let's see. That's going to give me 980 divided by 50. 822.3. Okay. So that is my T2X, which is also my T1. So that gives me one of my values that I need. Okay. My other value is this T2 that I need. Okay. There's a couple of different things I think we could do here. We could probably use, let's see, now that we know T2X, we could use, let's see if we could do it this way. We could use cosine of 50 equals adjacent, which is our T2X, or 822.3, because we just got that, divided by our hypotenuse, which is T2. And then we can just shift this around. We end up with T2 equals the same 822.3 divided by cosine of 50. And that's going to give me 1279 newtons. Another way you could do it, and I did it this way in the key that I posted, so this you'll kind of see it two different ways. Another way you could do it is, now you know this side, okay, and you know this side. So this side, T2X, is what we solved for at the beginning. And then T2Y is the same as FG. We could use those two sides and do Pythagorean theorem. That's, I think, a little messier than this way, but it would also work. And again, it's in the key, so you'll see it that way in the key. Okay, last one. We've got an Atwood machine, and this is based off the one I was using in class where I had my two little masses. So these are actually the mass of those masses. I made up the rest. So I'm saying it takes 2 seconds for it to fall, and I want to know displacement. So here I'm going to have a final kinematics and forces look. Okay. So let's glance at our equation sheet. For the Atwood machine, this is my acceleration. Again, I've derived this in another video, so I'm not going to go through that now. So I've got acceleration equals g times m1 minus m2 divided by m1 plus m2. And I'm kind of running out of time, so I'm going to put my 9.8 in here, my two masses. That's going to give me 3.3 meters per second. I'm skipping a few steps, but okay. I'm saying I'm falling from rest, so my initial velocity is 0. My time is 2 seconds that it takes me to fall. I know what my acceleration is. I want displacement, so I'm going to go for this equation. This is going to go away because my initial velocity is 0. So I end up with 1/2 times 3.3 times 2 squared. And that's going to give me 6.6 meters, which is a really long way. I don't know if it would actually do that or not, but I guess we could try it. But I'm just going back to these equations. I picked this one because I have initial velocity, I have time, I have acceleration, and I need displacement. Okay. So, all right, that is all the problems from class this week.